Liquefied hydrogen is the liquid state of the element hydrogen. It is a common liquid rocket fuel for rocket applications and can be used as a fuel in an internal combustion engine or fuel cell. A fuel cell is a device that generates electricity by a chemical reaction. Every fuel cell has two electrodes called, respectively, the anode and cathode. The reactions that produce electricity take place at the electrodes. Every fuel cell also has an electrolyte, which carries electrically charged particles from one electrode to the other, and a catalyst, which speeds the reactions at the electrodes. Hydrogen is the basic fuel, but fuel cells also require oxygen. One great appeal of fuel cells is that they generate electricity with very little pollution. Much of the hydrogen and oxygen used in generating electricity ultimately combine to form a harmless byproduct, namely water. One detail of terminology: a single fuel cell generates a tiny amount of direct current (DC) electricity. In practice, many fuel cells are usually assembled into a stack. Cell or stack, the principles are the same. The purpose of a fuel cell is to produce an electrical current that can be directed outside the cell to do work, such as powering an electric motor or illuminating a light bulb or a city. Because of the way electricity behaves, this current returns to the fuel cell, completing an electrical circuit. The chemical reactions that produce this current are the key to how a fuel cell works. There are several kinds of fuel cells, and each operates a bit differently. But in general terms, hydrogen atoms enter a fuel cell at the anode where a chemical reaction strips them of their electrons. The hydrogen atoms are now ionized, and carry a positive electrical charge. The negatively charged electrons provide the current through wires to do work. If alternating current AC is needed, the DC output of the fuel cell must be routed through a conversion device called an inverter. Oxygen enters the fuel cell at the cathode and, in some cell types like the one illustrated above, it there combines with electrons returning from the electrical circuit and hydrogen ions that have traveled through the electrolyte from the anode. In other cell types, the oxygen picks up electrons and then travels through the electrolyte to the anode, where it combines with hydrogen ions. The electrolyte plays a key role. It must permit only the appropriate ions to pass between the anode and cathode. If free electrons or other substances could travel through the electrolyte, they would disrupt the chemical reaction. Whether they combine at anode or cathode, together hydrogen and oxygen form water, which drains from the cell. As long as a fuel cell is supplied with hydrogen and oxygen, it will generate electricity. Even better, since fuel cells create electricity chemically, rather than by combustion, they are not subject to the thermodynamic laws that limit a conventional power plant. Therefore, fuel cells are more efficient in extracting energy from a fuel. Waste heat from some cells can also be harnessed, boosting system efficiency still further. Today, the main electrolyte types are alkali, molten carbonate, phosphoric acid, proton exchange membrane (PEM), and solid oxide. The first three are liquid electrolytes, the last two are solids. The type of fuel also depends on the electrolyte. Some cells need pure hydrogen, and therefore demand extra equipment such as a reformer to purify the fuel. Other cells can tolerate some impurities, but might need higher temperatures to run efficiently. Liquid electrolytes circulate in some cells, which requires pumps. The type of electrolyte also dictates a cell's operating temperature. Molten carbonate cells run hot, just as the name implies. Each type of fuel cell has advantages and drawbacks compared to the others, and none is yet cheap and efficient enough to widely replace traditional ways of generating power, such coal-fired, hydroelectric, or even nuclear power plants. Quite simply, a fuel cell is a device that converts chemical energy into electrical energy, water, and heat through electrochemical reactions. Fuel and air react when they come into contact through a porous membrane electrolyte which separates them. This reaction results in a transfer of electrons and ions across the electrolyte from the anode to the cathode. If an external load is attached to this arrangement, a complete circuit is formed and a voltage is generated from the flow of electrical current. The voltage generated by a single cell is typically rather small, less than 1 volt, so many cells are connected in series to create a useful voltage. A fuel cell is a device that uses hydrogen or hydrogen-rich fuel and oxygen to create electricity. Fuel cells are more energy efficient than combustion engines, and the hydrogen used to power them can come from a variety of sources. If pure hydrogen is used as a fuel, fuel cells emit only heat and water, eliminating concerns about air pollutants or greenhouse gases. Alkali fuel cells operate on compressed hydrogen and oxygen. They generally use a solution of potassium hydroxide, chemically CO, in water as their electrolyte. Efficiency is about 70%, and operating temperature is 150 to 200 degrees Celsius, about 300 to 400 degrees Fahrenheit. Cell output ranges from 300 watts W to 5 kilowatts kW. Alkali cells were used in Apollo spacecraft to provide both electricity and drinking water. They require pure hydrogen fuel, however, and their platinum electrode catalysts are expensive. And like any container filled with liquid, they can leak. Molten carbonate fuel cells (MCFC) use high-temperature compounds of salt like sodium or magnesium carbonates, chemically CO3, as the electrolyte. Efficiency ranges from 60 to 80%, and operating temperature is about 650 degrees Celsius (1200 degrees Fahrenheit). Units with output up to 2 megawatts (MW) have been constructed, and designs exist for units up to 100 megawatts. The high temperature limits damage from carbon monoxide poisoning of the cell, and waste heat can be recycled to make additional electricity. Their nickel electrode catalysts are inexpensive compared to the platinum used in other cells. But the high temperature also limits the materials and safe uses of MCFCs. They would probably be too hot for home use. Also, carbonate ions from the electrolyte are used up in the reactions, making it necessary to inject carbon dioxide to compensate. Phosphoric acid fuel cells (PAFC) use phosphoric acid as the electrolyte. Efficiency ranges from 40 to 80%, and operating temperature is between 150 to 200 degrees Celsius (about 300 to 400 degrees Fahrenheit). Existing phosphoric acid cells have outputs up to 200 kilowatts, and 11 megawatts units have been tested. PAFCs tolerate a carbon monoxide concentration of about 1.5%, which broadens the choice of fuels they can use. If gasoline is used, the sulfur must be removed. Platinum electrode catalysts are needed, and internal parts must be able to withstand the corrosive acid. Proton exchange membrane (PEM) fuel cells work with a polymer electrolyte in the form of a thin, permeable sheet. Efficiency is about 40 to 50%, and operating temperature is about 80 degrees Celsius (about 175 degrees Fahrenheit). Cell outputs generally range from 50 to 250 kilowatts. The solid, flexible electrolyte will not leak or crack, and these cells operate at a low enough temperature to make them suitable for homes and cars. But their fuels must be purified, and a platinum catalyst is used on both sides of the membrane, raising costs. Solid oxide fuel cells (SOFC) use a hard, ceramic compound of metal like calcium or zirconium oxides, chemically O2, as electrolyte. Efficiency is about 60%, and operating temperatures are about 1000 degrees Celsius (about 1800 degrees Fahrenheit). Cell's output is up to 100 kilowatts. At such high temperatures, a reformer is not required to extract hydrogen from the fuel, and waste heat can be recycled to make additional electricity. However, the high temperature limits applications of SOFC units, and they tend to be rather large. While solid electrolytes cannot leak, they can crack. Fuel cells don't need to be recharged. Fuel cells are more efficient. Fuel cells only produce water as the waste product. Fuel cells don't need to be recharged as long as they are constantly being supplied with hydrogen and oxygen. The electrodes are separated by an anion exchange membrane that allows anions to pass through but not hydrogen and oxygen gas. Why do we need fuel cells? Fuel cells can eliminate pollution caused by burning fossil fuels. For hydrogen-fueled fuel cells, the only byproduct at point of use is water. If the hydrogen comes from the electrolysis of water driven by renewable energy, then using fuel cells eliminates greenhouse gases over the whole cycle. Disadvantages of using fuel cells in cars. These include, hydrogen is in the gas state at room temperature and pressure, so it is difficult to store in the car. Fuel cells and electric motors are less durable than petrol engines and diesel engines, so they are not so long-lasting. Fuel cells are very expensive. How long does a hydrogen fuel cell last? H2 fuel cells currently in production have a life expectancy of from 5,000 to 10,000 hours. If we apply that to an average driving speed of 45 miles per hour, a combination of in-town on highway driving, we should expect to get 225,000 to 450,000 miles. What is the fuel in a hydrogen-oxygen fuel cell? Fuel cells. A fuel cell is a device that converts chemical potential energy stored in molecular bonds into electrical energy. A PEM proton exchange membrane cell uses hydrogen gas H2 and oxygen gas O2 as fuel. The products of the reaction in the cell are water, electricity, and heat. Where can fuel cells be used? Fuel cells are used for primary and backup power for commercial, industrial and residential buildings and in remote or inaccessible areas. They are also used to power fuel cell vehicles, including forklifts, automobiles, buses, boats, motorcycles and submarines. Fuel cell efficiency. If the fuel cell is powered with pure hydrogen, it has the potential to be up to 80% efficient. That is, it converts 80% of the energy content of the hydrogen into electrical energy. However, we still need to convert the electrical energy into mechanical work. Why is fuel cell better than battery? Hydrogen used in fuel cells has an energy-to-weight ratio 10 times greater than lithium-ion batteries. Consequently, it offers much greater range while being lighter and occupying smaller volumes. It can also be recharged in a few minutes, similarly to gasoline vehicles. Why is a battery called a cell? A chemical reaction takes place in the battery when it is discharged that produces a flow of electrons out one plate on the negative side and into another plate on the positive side. Actually, a single unit of a battery is a cell. A battery is called a battery because it is a battery of cells together. What are the problems with hydrogen fuel cells? The only real problem is the issue of safety. Hydrogen is highly flammable, more so than regular fuel, and is harder to contain than oil. This means that any car fitted with a hydrogen fuel cells is a lot more likely to blow up or set on fire if it is exposed to extreme heat, if it breaks down or if it overheats. Can a normal car engine run on hydrogen? Internal combustion engines can be modified to run on hydrogen gas. A battery storage cell is a galvanic cell or a series of galvanic cells that contains all the reactants needed to produce electricity. That wasn't designed for it. In contrast, a fuel cell is a galvanic cell that requires a constant external supply of one or more reactants to generate electricity. How do we get hydrogen? Hydrogen can be produced from natural gas, coal, biomass and oil. And it can be produced from renewable energy sources such as wind, solar, geothermal and hydroelectric power. Hydrogen can even be captured from waste from industrial processes.